All right, as we're looking at various ways of integrating, other methods of integration in this unit, we looked at integration by U substitution. We're going to look at integrating some different functions that we haven't handled before. But one method that we're going to use is actually called the trapezoid rule, or the trapezoidal rule. Okay? And the idea is very similar to what we did with Riemann sums. Okay? It's very similar to what we did with Riemann sums, but instead of rectangles, we're going to use trapezoids. Okay? So let me show you what we're talking about here. Let's say that we have this function, x cubed plus 1, and you'll notice what we've done is I have x sub 0 is 1, and x sub 1 is 2, and I want to approximate the area underneath the curve of x cubed plus 1. So to do that, rather than do lower rectangles, where I miss out on some stuff, and rather than doing upper rectangles, where I get some extra area, we're actually going to use a closer approximation by doing the trapezoid. Okay? Now, that's the trapezoid we're finding. Now you can see here, because it does curve a little bit below, we are going to get just slightly over the actual area here. Okay? But we're going to get really close. Okay? In fact, if I were to do the integral from 1 to 2 of x cubed plus 1, I would have x to the 4th over 4 plus x evaluated from 1 to 2. Okay? And if I did that, okay, that would be a 16 over 4 plus 2 minus 1/4 minus 1. Okay? So that would be 6, 5, 4 3/4. That's what it actually is, the area under the curve. However, I can approximate that using this trapezoid. And what is the area of a trapezoid? What's the formula for area of a trapezoid? Okay, the sum of the two bases times the height divided by 2. There you go, good. All right, so the area is 1/2 times the height times the sum of the bases. Now, the bases are the two sides that are parallel. So in this case, that's going to be this side and this side. All right, we'll call this base 1, and we'll call this side base 2. Okay? Height is always the distance between the bases. All right? Yeah, and that's the distance between 1 and 2. That's our height. Okay? So if I'm finding this area, I'm going to do 1/2 times the height. The height is 2 minus 1. Okay, or just 1. And then if I want to find base 1, I need to actually take f of 1, right? Because whatever that function equals when x is 1 is going to be how tall this side is. All right? And to find the other base, I'm going to do f of 2, because that's the x value that will give us the other height, okay, or the other base, I should say. Okay? So I have 1/2 times 1 times f of 1 is 1 cubed plus 1, so that's 2, plus f of 2. 2 cubed is 8 plus 1 is 9. Okay? So I get, in this case, 11 times 1/2, which is 5 1/2. Okay? Relatively close to 4.75, but as you can see, we got a little more than the actual area under the curve. Okay, so you might say, well, what's the point in doing this? How do you think we could get a more accurate representation of the area under this curve? Add more trapezoids. That's right. Okay, just like with the rectangles, the more rectangles we added, the more accurate our approximation was. Okay? And that's what we're going to end up doing. Okay? Now, why would we put ourselves through this? Okay? We already have Riemann sums, but as you saw, there were certain ones that were either much more difficult, or there were even some that were impossible to do, where you had to get the sums down to the sum of the i's, or the sum of the I squareds, or the sum of the I cubes. You had to get real creative, and sometimes it was possible, sometimes it may not have been. Here we have some functions at the bottom that we don't have any antiderivative rules for, so we can't use f of b minus f of a. And we don't, doing it with Riemann sums may or may not work in these cases either. So we're going to actually use trapezoids. Now, again, notice what we're doing here. We're evaluating a definite integral here. Okay? These don't have an antiderivative, so we can't do the indefinite integral. But we can do the definite integral. And let me just show you. Here's the rule. If f is continuous on a closed interval from a to b, the trapezoidal rule for approximating the integral from a to b is that whole thing. I want to pick that apart so that we understand where all these pieces come from, and it actually is not too hard to do if you understand it, okay? So let's first of all look at this b minus a over 2n, okay? Well, if we remember what the formula for area of a trapezoid is, it's 1/2 times the height times base 1 plus base 2. Well, this b minus a over 2n is the 1/2 height. Okay? The 2 comes from the 1/2. The b minus a over n is the height. All right? If we zoom in over here, looking at this, b minus a is the whole length of that interval. Okay? If n is how many trapezoids we want to use, okay, n equals the number of trapezoids, then to figure out how wide we need to make this, we're going to take that b minus a and we're going to divide it by n. And that's going to be the width. You remember we did that for delta x back with our Riemann sums. It's exactly the same thing as we're doing here. Okay? So that's b minus a over n for all of these. Okay? So that's the first part of the formula. That's why we have b minus a over 2n, because it's 1/2 times the height. So where does all of this stuff come from? All of the f of x sub 0 plus 2f of x sub 1 and so on. Well, let's go back and examine each of these rectangles. Okay? If I look at this one here, okay, I've got my base 1 is going to be whatever f of x sub 0 equals, right? And my base 2 is going to be the length where f of x sub 1, okay? So the area of that trapezoid is going to be 1/2 times b minus a over n times f of x sub 0 plus f of x sub 1. Okay? Now let's look at the second rectangle. Okay? Or not rectangle, trapezoid. This trapezoid I'm highlighting or outlining in green here. You'll notice it also has a height of b minus a over n. So I've got 1/2 times b minus a over n. Oh, not a, n. Okay. Times, well, this side right here is the f of x sub 1. And then the other base is f of x sub 2.
So why don't they overlap? Like in the formula, wouldn't they overlap and count as twice?
Well, we are not, there's no area actually being counted twice because a line doesn't take up any area, okay? But you could see if we put these two together, they have a common factor of b minus a over 2n, all right? Let me put these together here. If I were to add them together, they have a common factor of b minus a over 2n times f of x sub 0 plus f of x sub 1 plus f of x sub 1 plus f of x sub 2. And that's just for those two, but you can see here, you know, this is where the 2 comes from in our formula. Okay? And you guys can, I'm sure, see if we were to do the third one, it would have an f of x sub 2 as one of its bases. So now we would have 2 f of x sub 2's. All right? If we did the fourth trapezoid, one of its bases is f of x sub 3. So now we would have 2 f of x sub 3's, and so on. So that's why our formula here, you'll notice each end is only used once, f of x sub 0 and f of x sub n. But all the middle ones are used twice because they're the base of one trapezoid and they're the base of the next trapezoid. Okay? Once you get that idea down, this actually is a pretty simple method to use. Okay? Now, as we did with the Riemann sums, as the number of trapezoids approaches infinity, this sum is going to approach the actual value of the integral. Okay? So, we can you know, just make n bigger and bigger and bigger, and we can get closer and closer and closer of an approximation. Okay? By the way, when your calculator does integrals, it uses a method like this. It doesn't know all the rules that we know, even for things that we have rules for. It's usually using some kind of a limiting process like this. Because calculators or computers in general are really good at doing real tedious calculations fast. Okay? So let's do this a couple of times here. I want to work through one. Here we're going to approximate the integral from 0 to pi of sine of x dx. Okay? You might say, well, I already know what the integral of sine of x dx is. It's negative cosine. And you'd be right. Let's actually go ahead and find that just to see what our answer should be, and then see how our approximations go. Okay? So if I'm doing the integral, let's get to a pen. The integral of sine of x dx from 0 to pi, and that's a negative cosine. Evaluated from 0 to pi, I'm going to have a negative cosine of pi, which what's cosine of pi equal? Negative 1. So that's a negative negative 1, which is going to be positive 1, minus a negative cosine of 0. What's cosine of 0? 1. So it's minus a negative 1. So our area should equal 2. Okay? The area should equal 2. Let's work this out with, first of all, 4 subintervals and then 8 subintervals. Okay? Oh, here. Yeah. Okay? So, if I'm breaking this interval from 0 to pi up into 4 subintervals, then my b minus a over n is going to be pi minus 0 over 4, or just pi over 4. Okay? It's pi over 4. So if I'm starting at 0, notice here this one's already drawn for us. I have 0, pi over 4, 2 pi over 4, 3 pi over 4, and then here at the end 4 pi over 4. Okay.
Wasn't it 2n?
Yeah. 8.
You wrote it.
Isn't it b over a minus a over 2 and b minus a?
In the formula, yeah, I was just finding the width at this, or the height at this point. Yes, you're right. The formula calls for us to use 2n in the end. All right, so, but at this point here, all we're doing is we're finding those separations, okay? And that's important because to find bases for the trapezoids, I've got to use f of 0, which in this case equals sine of 0, which is 0. I've got to do f of pi over 4. Well, sine of pi over 4 equals root 2 over 2, okay? Root 2 over 2. F of pi over 2. What's sine of pi over 2? 1. F of 3 pi over 4. It's just root 2 over 2. And then f of pi is 0. Okay?
Why do we start on the f0? Because I thought, isn't the outer one a triangle?
Well, they are. But because we're using the trapezoid rule, a triangle, you may have looked at this back in geometry class or not, but a triangle is just a trapezoid where one of the bases is 0. Okay? If you think about it. So that's what we've got on the end. We've got a trapezoid where one of the bases is 0, i.e. a triangle. Okay? But it'll still work in our formula. So if I've got 4 subintervals, then I'm going to approximate this area by taking b minus a over 2n, so it's going to be pi over 8, okay, pi over 8 times, and then I have the f of 0, which is 0, plus 2 times the f of pi over 4, so 2 times root 2 over 2, plus 2 times f of pi over 2, which we said was 1, plus 2 times f of 3 pi over 4, which is root 2 over 2, plus just 1 of the other end. F of pi is 0. Okay? So notice base 1 plus base 2, base 1 plus base 2, base 1 plus base 2, and we put all the bases together. Some of them are used twice. All the middle ones are used twice. Okay? So we now have pi over 8 times root 2 plus root 2. Okay? So that's 2 root 2 plus 2. Okay? So pi over 8 times 2 root 2 plus 2. And we could distribute that pi over 8 in if we want. And that'll give us pi root 2 over 4 plus pi over 4. Okay? Now, if you use a calculator and figure out what that equals 1.896. 3 decimal places, because AP wants us to do everything to 3 decimals. Okay? Now, we said that we were supposed to get 2. We can see that we're pretty close. All right? Also, looking at the trapezoids, it makes sense that we're a little bit under, because there's a little bit of that curve that's sticking over our trapezoids. Okay? So, as we said, if we wanted a closer approximation, we should use more trapezoids. Okay? So let's get started on this one, and then I'll let you guys finish it. If I wanted to do n equals 8, okay, notice the b minus a over n is going to be pi over 8. All right, so I come over here, and here's pi over 8. Okay, well here, I'll label it down here, pi over 8. 2 pi over 8. 3 pi over 8. 4 pi over 8 is pi over 2. 5 pi over 8. 6 pi over 8 is 3 pi over 4. Then we have 7 pi over 8. And then pi. Okay? So you'll notice here the trapezoids, if we're looking at it, you can see as I draw it, there's really very little left as far as we can see that's not being accounted for. There is a little bit, but even just doubling it to 8 trapezoids, there's just a tiny little bit here that we're going to miss out. So this should be a more accurate thing, okay? Now, we already know what these ones are, but these are not on the unit circle, the pi over 8, 3 pi over 8, and so on. So you will need to use your calculator for that. So take a couple minutes here, set up your formula, and find these values, make sure you're in radians, and see if you can come up with the result. Okay, so now that you worked through it, let's look at the steps here. You've got to figure out what sign of the pi over 8, the 3 pi over 8, 5 pi over 8, 7 pi over 8 are. Okay. And then you're ready to set it into your formula. Okay. Now, the b minus a over n was pi over 8, so if it's over 2n, that means it's going to be pi over 16. And then we have your endpoints, okay, or your bases. The first one is 0 plus 2 times 0.393 plus 2 times root 2 over 2 plus 2 times 0.924 plus 2 times 1 plus 2 times 0.924 plus 2 times root 2 over 2 plus 2 times 0.393 plus the last one was 0. Okay? The first and last are not always going to be 0. It just happens to be on this time. Okay? So, did you get that? What did you end up getting?
1.975.
975? That's pretty close to 2, isn't it?
I got 1.971.
Okay.
But I rounded. Oh yeah, well, I did the same thing as you. I rounded the like for the f of pi over 8, I rounded it.
Okay. Yeah, and if we can avoid rounding as much as possible, that would be good, okay? Yes.
Could you just do half of it, multiply times 2?
Yeah.
The only thing, okay, that's a good idea. The only thing to be careful of is that middle one, the 2 times 1.
Wait, what did you
He recognized on this one, because sine is symmetrical,
Oh,
if you did half of it and then doubled it, as long as you didn't count that 2 times 1 twice, then yeah, that would work. Okay? Let me back up a little bit though, and let's look at how you could do this on the calculator effectively. Let me bring up camera. Okay, so let's look at how we would do this. First of all, notice that the ends here, the first thing we're going to do is store all of the angles that we need to use, okay? And I'm going to do that with a list, all right? Now, lists, you use these curly brackets that are above the parentheses, okay? So, second parenthesis puts that little bracket there, okay? And what I'm going to do is I'm going to put in all of the angles separated by a comma. So 0, pi over 8, comma,
Where's the comma?
pi, it's to the left of the parenthesis, pi over 4, comma, pi, or sorry, I should have a 3 pi over 8, 3 pi over 8, 4 pi over 8, which is pi over 2, 5 pi over 8, 5 pi over 8, comma, 6 pi over 8, which is 3 pi over 4, comma, 7 pi over 8, comma, and then pi. All right, and then I'm going to put a closing curly bracket on there. That's above the right-hand parenthesis, second right parenthesis, okay? Now, I need to think about what I need to do with each of these, okay? I'm going to store this, first of all, just so I don't lose it accidentally. I'm going to hit store, the STO, and you'll notice above the number 1, there's L1. I'm going to hit second L1, okay? And you should see a little arrow with L1, hit enter, and now I've stored all those values. So you notice it actually converted the pi over whatever to decimals, and that's okay, all right? So now I've got to think about what I had to do with each of those. I had to take the sign of each of those, right? So guess what we can do? I can hit sign of L1. And guess what that'll do? When I do an operation, parenthesis, if I do an operation like this on a list, it'll actually do that operation to every element in the list. So if I did 2L1, it would multiply all of them by 2. Okay? Yeah.
So put it in the parentheses and then you highlight it and you hit store list 1.
You just hit store list 1, yeah.
Do you have to hit enter first?
No, don't hit enter. I mean, you can hit enter, and then,
After the end parentheses, you just hit store.
yeah, after the last curly bracket, hit store L1. It'll store it in there. Okay, so now I'm going to do the signs. Okay, and now I have the signs of all those angles. There's the 0.707, that's root 2 over 2, and so on, okay? And by the way, if you want to see all of them, you can hit the right arrow and it'll scroll over. There's the 0.924, the 1, the 0.924, the 0.707, the 0.3826, and so on, okay? Now, I needed to then multiply all of them except for the end ones by 2. So, I'm going to do times, and I'm going to multiply it by another list, okay? So, if I multiply a list by a list, or if I do any operation with a list by a list, they have to have the same number of things in each list, okay? And what it'll do, instead of doing the same thing to all of the things, like when I did sign of the list, if I do a list times a list, it'll do the first one times the first one, and the second one times the second one. So, I want to make a list where I'm going to multiply the first one by 1, and then all of the other ones by 2 until I get to the last one. I just have to keep track that I get the right number. So there were 1, 2, 3, 4, 5, 6, 7 middle ones. So I have a 1, and then I have, let's see, that's 4, 5, 6, 7 2s, and then another 1. Okay? That'll take care of the 1 times the first one, 2 of the second one, 2 of the third one, 2 of the fourth one, 2 of the fifth one, and so on. Does that make sense? Okay? So now I hit enter. Okay? Hang on, you just walked in, so you're going to be totally lost, and that's okay. All right.
If
Right.
the second list I just put it in 8 numbers, will it shows error?
It'll give you an error if you put the wrong number of things in. Yeah.
Wait,
Okay.
mine, like, I'm hitting store list and it's not going.
I'll look at yours in a sec, okay? All right, so now you have all the values that you need, and what do you need to do with all these?
Enter. Oh, store. Sorry.
Now, what do we have to do in the parentheses? We got to add them up.
Okay.
We've got to add them all up. So that's where, if you go into your list menu above stat, I hit second list and hit the right arrow over to math and look at number 5. Number 5 is the sum.
Where's the list? Second.
Okay, it's under second stat.
Oh, stat.
Okay, so I'm going to do the sum of that previous answer. Well, the answer, remember, is above the negative sign, so I hit second answer. Okay, so everything in that set of parentheses equals 10.05. All right, so going back, I had pi over 16 times 10.054, 6, 7, and so on. So all I've got to do now is multiply by the pi over 16 times pi over 16, and I got 1.974.
I feel like just writing it out is easier.
If it's easier for you, go for it. I think if you guys tried it a few times and you got the hang of it, it's not too bad. Okay? So, that's how you can do it with the calculator. So to wrap this up, I just want to make a comparison with the method we used before. Okay? If we did the midpoint Riemann sums, okay, the Riemann sums using the midpoint, that was this first formula here. And notice what we're doing there is we're averaging the x coordinates and then finding the y value of that, okay? So right here, we're averaging x coordinates and finding the y value in the middle of the rectangle, okay? Here, we're not doing that. Because we're using trapezoids, we're actually averaging the y coordinates on either side of the trapezoid. And that gives us a slightly different result, okay? So that's kind of the difference between what we did with the midpoint Riemann sums and the trapezoid rule, okay? So that was just the last thing I wanted to mention to kind of sum all this up.